Hey everybody, welcome. This is the video for video analysis of centripetal motion. This is a lab that's going to use the same software that we used when we were throwing around those balls with free fall and bouncing and all that, except we're doing circular or centripetal motion this time around. So our sort of starting point here is to imagine, you might want to look at your lab manual for a better picture, that you're holding a ball and it's attached to a string. I'm not going to even attempt to draw a hand there. And you are spinning this ball around in a circle, right? So we have this nice circular motion. And we want to think about what this ball is doing, how it's accelerating, what are the forces on it, all of that. So we'll give the ball some mass m. It's going tangential. The velocity is tangential to its motion. Okay, so we have our velocity vector going that way around the circle. Our circle has some size, right? We give the circle a size of a radius. And what's going to be important for us today is that there is this force. If you have a ball on a string, there's going to be a force that is due to the tension in the string, okay? But centripetal forces are interesting in that it's not always a string that's providing centripetal force. It can be gravity or all kinds of different things. Centripetal just means that it is center seeking. So, and hold on to this because this is important later, it may not even be the total force, it might just be a component of the force that seeks the center. Okay, so let's start with some of our basic equations. You got to remember a few things here, like Newton's second law, right? That force equals mass times acceleration. When we're talking about centripetal force, I'm going to give this a little subscript of r. That's radial is another way to think about that. This, whenever you see the FR, think centripetal. Okay, it's in the r direction, radius. Okay, and our acceleration is also in the r direction. We have this centripetal or radial acceleration. If you see in your lab manual there, we can think of that acceleration in terms of the velocity of our ball in this case and the radius. The centripetal acceleration is just the velocity squared divided by the radius. Okay, so what is velocity? Let's take a minute and think about that because we got this circular motion here. Velocity is still distance over time, right? It still has the same type of units, the same meaning in that way. But what does distance mean when you're going in a circle? Well, we divide the distance by how many circles it makes. So for us, when we're talking about this circular motion, we're thinking about how big is the circle. So our distance is the circumference, 2 pi r, right? That's the circumference. And I'm not going to have enough room to write the whole word circumference. Divided by the time it takes to go one period. So we think about this in terms of a single circle. We set our velocity by the time it takes to go a single circle. And so that is our period. Okay. So we have special ways, but it's not all that different from what you've seen before. It's still Newton's law. It's still velocity is distance over time. Just have a special distance and a special kind of time. Let's think about that period and that idea of that motion here a little bit. So this is actually simple harmonic motion. We have seen this before. We didn't really talk about it, but simple harmonic motion is the same motion we saw in the very early lab we did on the pendulum. Here, I'm trying to write pendulum. Uh, simple harmonic motion. Remember that pendulum that swung back and forth, and we were relating its motion to the length of the pendulum? Here, we have the same idea. We have a ball going in a circle and it keeps coming back to where it started. If you graph simple harmonic motion in a displacement, I'm running out of space here, displacement versus time graph, it looks a lot different than when we were doing free fall, for example. Simple harmonic motion repeats. And it repeats in a specific way that you might recognize here as a wave or a cosine function. Mine is not as pretty as the one that's in your lab manual, but the idea is the same, that that ball, as it moves around the circle, here's our circle again, our ball moves around the circle, and as it does, it's going to eventually come back to where it started, right? So that ball is going to move around the circle as time goes on, and eventually is going to come back to where it started. You have to think of displacement in this case in terms of radius, okay? How far is that ball moving away from the center position? What is the radius? You can relate this when we're talking about a wave function. The radius is also the amplitude or the height of the wave. So you're going to see this when you make graphs today. Your Logger Pro will spit out these beautiful wave functions. And remember, the radius, how far it goes in any one direction, is equal to the amplitude. Notice the radius here is positive or negative. It's kind of weird to think about it that way when we look at a picture flat face on like this. But think about, and this is what you're going to be doing today, looking at this edge on. I'm not as good at drawing it here. Let me keep my colors the same. I'm not as good at drawing it edge on, but here's the idea that you have something going around in a circle. Now we can kind of see the edge on view. Let's get our ball in there. It's going to move around the circle. Sometimes it's over here, and it's eventually going to come back to where it started. The radius is right here. So if you think of that edge on view, what you're really going to see is the ball going back and forth as it goes around the circle. And you'll see this in your video too, because I want you to get an edge on view on your video. So as you see that, you'll see the ball with time going back and forth, right? It's spread out in time, but that's the idea, okay? And radius is half of that motion as it passes that origin. Okay, so that is how we think about the distance. Now let's not forget, good thing we have lots of colors here. Let's not forget time. Remember we said we're going to say the time is the amount of time it takes to take one complete circle, or the period. Again, for us, I'm going to use different spots on my curve because I'm getting all crazy here. It is the time it takes to go back to where it started. If I draw over these 2 points, back to where it started. You might recognize this period, the time it takes to go back to where it started, as a wavelength. The distance from crest to crest, or from trough to trough, peak to peak, trough to trough. Okay? So we're stretching our idea of what a displacement versus time graph looks like when we get circular, centripetal, simple harmonic motion. Okay, Now we're going to add a complication. Don't you always love it when we add complications? You're not going to be looking at that nice flat two-dimensional case. We are going to add in an angle. So I'm going to be asking you to swing your ball at an angle. So the ball is going to go around in a circle, right? Here's the motion of our ball going around in the circle. Your hand is going to be up here at the top. Remember, I don't draw hands. Um, so I'll make another video of me actually demonstrating this in person. But the idea is here that instead of just having that nice face on view, you have an angle. And you have to be careful about which angle we are talking about here, because when we do a triangle, see there's the center, we still have that radius away. We have a couple of different angles that we're talking about, so be careful if you're doing problems similar to this on tests or quizzes or whatever. I'm going to call this angle here theta, and I'm going to call, just so that we're very clear, this angle up here beta. And beta is 90 degrees minus theta. So those are two different angles, right? This is a 90-degree angle right here. So there's our triangle. We're all oriented. Here's our ball. We're going to need to know the mass of our ball. If you borrow one of our balls from Nichols, then I can tell you what the mass is. If you use a ball at home, you're going to have to figure out a way to find the mass. You can bring it up here and weigh it or something. Okay, anyway, that's a side note. What we need to focus on here is what is going on with the forces. So we have, remember I said centripetal force is center seeking. I'm going to pull our picture out to the side here. Here's our ball, right? We still have a string attached, okay, up this way. So that string is providing some tension force, right? I'm going to call that F sub T. That's the tension. And that goes along the string. I'll draw it on this picture too. However, that's not the only force that our ball is experiencing. Our ball has a mass. That's why I said it has a mass, right? And so it has a weight, right? We have a weight on the ball, and that goes down. Remember, weight is mass times gravity. These are the only two forces on the ball. We neglect air, like always. So my question to you all is, where's the centripetal force? In the first case, where we had this flat, two-dimensional motion, y'all remember? The centripetal force was towards the center, right here. And it was equal, in that case, to the tension. Right here, the tension is the centripetal force. But now I've added this angle in. Centripetal force is always center seeking. Where's the center of our motion? It's along the radial direction, along the radius towards the center of the circle. So my centripetal force is here. Now, did I just make up that force? No. Centripetal force is not its own sort of category of force. It's whatever part of the real physical forces, in this case we have tension and weight, is center seeking. So what we need to do is to break our tension into its components. And remember our vector lessons, right? So when we're looking at this tension, it's got two components, and I don't have enough colors for all this, right? A tension vector has two components, one this way and one this way. This is the force of tension in the y direction. Okay, now this is why I was careful with my angles, because I want it to be, oops, that came out funky. I want it to be clear what angle I'm talking about when I break this up into its components. This is the force of tension times the sine of theta. Remember theta? That's that angle down at the bottom. And Ft cosine theta is my x component. So this is y and this is x. It's my x direction and my y direction. Now we can answer the question, what is my centripetal force? My centripetal force then is equal to the x component of the tension, Ft cosine theta. All right, guys, you following that? So what you're going to need to do is when you're doing your various measurements, let me just get a clear picture here. I'm going to redraw this super quick so I can show you a couple of things. Okay, there's the circle. Remember, this is our angle theta. This is the ball right here. So you're going to need some measurements in order to figure everything out. The first measurement you're going to need is the mass of the ball. Use one from school. Come check it out. Or you can borrow one of our balances to get the mass of whatever your ball is. You're also going to need to know this angle, theta. In order to know that, you can measure the length of the string that's attached to the ball. So notice when you get to your data sheet, this L is going to be the length of the string plus the radius of the ball. If you have a large ball, our ball is not huge, but the radius makes a difference, plus radius of ball. In other words, it's the entire length, the entire hypotenuse of that triangle there. Okay, so you need to know length and you need to know mass. And in order to figure out the angle, right, we're thinking through our trig. We're thinking, oh yeah, I remember now. If I do inverse cosine, I can figure out the angle if I have two sides of the triangle, the hypotenuse L, which I just told you all to measure, and the radius of the circle. That is trickier, y'all. We're going to actually use the software, Logger Pro, to find R. Okay, use Logger Pro for R. How do I find R with Logger Pro? Well, guys, look at this. You're totally going to make a displacement versus time graph and figure out what the amplitude is. Okay, so that's how that is all connected there. So when you look at your data sheets, you will find that you measure the mass of the ball and the radius. Then you're going to plot position versus time, x versus time, and find R. You can also, let me go back to that again, you can also find period. Notice from your graph, it's just the wavelength. Yes, I do want you to do that, but we're also going to calculate it. So let me get a blank piece of paper here. The point of today's lab is to figure out to calculate the period, calculate t, and compare to what you found in the graph. Compare to t from your plot. This means when you get to the calculations section and you're reading through the procedure and you're looking at your data sheet, that you cannot use t to calculate t. Do not use t from the plot, not to calculate t. Because guess what? If you do that, you'll get a 0% difference because you just calculated what you plotted. All right, that is not what we're looking for. We want to calculate t and compare it using percent difference. So when you get to the calculations, do the calculations in order. Show your work. All right, so show work, do calculations in order on the data sheet. Okay, and I'm going to briefly go over some of what you're going to need to know. I've already given you the basics, you just don't know it yet. So when you get to those calculations and that analysis, this is what you need to know. You need to know, let's do our force diagram again. Okay, so you need to remember, and I don't remember all the colors that I used, y'all, you're just going to have to go back to that prettier plot. We need to remember that in the positive y direction, we have the tension force, oh, there it is again, sorry, sine of theta, the y component. In the x direction, we have the tension times the cosine of theta. And going in the negative y, we have the weight, which is equal to mg. All we're going to do is recognize that we know a lot in this, and we can solve these various equations for what we know. What we know, for one, is when we look at the forces in the x direction, we know, we just said, that in the x direction we have ft times the cosine of theta. We also know, go back to that other pretty picture with all of the colors, that that is our center-seeking force. So that's also our centripetal force. We also know that, I'll just put it underneath here, that our centripetal force is equal to mv squared over r. All of these things are equal to them, right? You can make various equations out of all of those equalities. Think about what you know and use the equations, right? Do I know the tension force? I don't know. Do I know the angle? Oh, maybe I can figure out the angle. Do I know the radius? I do know the radius. So you have various pieces of that that you know. Use that. Let's look then in the y direction. We also have information in the y direction. So in y, we have two different forces going on, but we also know that those two are equal. That ft sine theta is equal to the weight, or another way to look at it, that if I subtract the weight, it equals 0. How do I know that? How do I know that they're equal, or how do I know that they're equal to 0 if I subtract it? Because our object is not accelerating in the y direction. Okay? Think about it. Where is it going in the y direction? It's not. It's only got stuff going on in x, or in our case, the radial direction. Okay? So again, think about what you know. You can rearrange this equation. Remember that weight equals mg, and so then you could say, okay, well, if I rearrange, then Fw equals Ft sine theta, etc., etc. You guys can do this. This is not that tricky. You just have to put your thinking caps on, follow my hints. My hints being, do the calculations in order, and think about what you know. Okay? You're going to do this twice for two different lengths. You're going to calculate t and find the percent difference from the plot. Okay, I am going to stop there. I will see you on the other side.